Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem subset sum 2 from the SDE sheet. But before we move on to the problem, if you are new to our channel, please do consider subscribing to our channel. So the problem states that you're given an array nums and it may contain duplicates. Now your task is to return all the subsets, but the solution set should not contain duplicate subsets, and you can return the solution in any order. Like for an example, if you see this array 1 2 2, so you can have 8 subsets. We have already done this problem in our previous video where the problem was subset 1 and we had to print all the subsets, and we saw that it if n is 3, it will always have 2 to the power 3 subsets. But over here it has been said that you cannot have duplicate subsets, so that is why we have to ignore all the duplicate subsets. So these will be the subsets for this given array. So if this question comes up in an interview, the first solution that you'll give to the interviewer should be the brute force, where you'll tell the interviewer that you're going to use the pick and non-pick technique to generate all the 2 to the power n subsets, right? So if you don't know the pick and non-pick technique, you can go back and watch my previous video where I've solved the subset 1 problem, which will help you to generate all the subsets. So once you have generated all the 2 to the power n subsets, now this will give you all subsets. It will also have duplicates. So how do you remove duplicates? Obviously, you put all those 2 to the power n subsets into a set. So once you put them into a set, all the duplicates will go away and you will only have all the unique subsets. So again, you can just convert this set into a list of list or a vector of vector and return this, and this will be your answer. So after recursion, yes, after recursion, you're using an extra time. Yes, you're using an extra time of converting it into a set and then again reconverting it back into a list of list. Now you know the number of subsets is 2 to the power n. So your set size will be 2 to the power n. So if you're putting every element into the set, you know, it's going to take m into log m in set. So where m will be 2 to the power n, right? That will be the size of your set. So that's the extra time that you are taking to put it into the set. So the interviewer will obviously not be happy with the extra steps that you're using of putting it into the set, and he'll ask you to optimize it in the recursion itself. So yes, now it's time to understand how can we optimize the recursion so that we leave out all the duplicate subsets and we only get the genuine subsets. So since Unacademy has sponsored this video, let me introduce you to the Learn CP initiative that they have taken up. So you will basically get live interactive classes, right? Where you can attend live interactive classes with the top educators and you're free to interact with them via messages, emojis or whatever you want, right? And with this you'll be getting relevant questions on every topic which you can practice directly at CodeChef. So you'll be getting a set of curated problems. Right after that, if you're having any doubt, yes, if you're getting stuck at any problem post class, you'll also be getting a doubt panel, right, which will have experts who will be solving your doubts. So these are the things which Unacademy will be offering you. So they're launching the batch Ascent, which is starting on March 4. Now this batch is called Ascent because it's relevant for all the intermediate level programmers. It will be starting with the intermediate data structures, algorithms like STL, merge sort, counting inversions, binary search, before actually moving on to the advanced topics. So you can check out this batch. This is being taken by Arjun and Nishchay. So if you're willing to take up the batch, you can probably check out the subscription plans. And if you take up a subscription plans, you will get access to all the courses, be it future courses, be it past courses, everything on their platform. And yes, if you're taking up a 6 months or a 12 month subscription, you will also get the CCT SAP certification exam free, right? So go check it out, and if you feel like enrolling it, you can. And yes, if you want an additional discount, you can use the coupon code take you forward to get an additional 10% discount. So now let's talk about the recursive solution, where we can actually put in the logic such that the duplicate subsets are not generated. So we are going to write a recursion in such a way that at every step it generates a list. Yes. So the first step will be carrying an empty data structure. So if I'm carrying an empty data structure at the first step, that means I am generating a zero size ka list. So I've generated a zero size list. So that's the null list that is getting generated. And I'm going to start with the 0th index. So this is the first recursive call that you'll make, which implies that you have generated a list of size 0. Now if I ask you, you have to generate a list of size 1. So what are your options? What are your options of generating a list of size 1? You can say that you can pick this 0th index. Yes. So if you decide to pick this 0th index, your data structure will only have this value at the 0th index 1. And as I said, every time you call a recursion, think that you're generating a list of the size 1, or the second recursion call will be a list of size 2, and so on. So I can say I generated a list of size 1 which is containing 1. And since you have picked up 0, you moved on to the next index, that is 1. So this is a recursion call made. If you're calling this recursion, what you can say is you generated a list of size 1. So this is the list. What other options do you have of picking a single element in a list of size 1? I can say I could have also picked this 2. So if you decide to pick this 2, I can say I generated a subset which is having only 2, and that is again a list of size 1 that I am generating. So if I've decided to pick this first index, obviously I cannot pick at the next instance anything among them. So I will just move to the next index, that is 2. Now, can I pick this 2 again? Now understand this. This is where your logic comes in. So if you decide to pick this 2 again, what kind of list will you get? You will again get the list of size 1 which is containing 2. So that will actually generate a similar list which you would have already generated. So this is where you're going to plant your logic, saying that I'm not going to take duplicates, right? I'm not going to take duplicates. So this was a duplicate, so I don't take it. So when I'm trying to create a list of size 1, if I've taken 2 once, let's not take it once more. So I don't take it. Can I take this 2? No. Will I take this 2? No. Can I take this 3? Yes. So if you decide to take this 3 up, you will create a list of size 1 which is having 3. So you got a unique list again. So since you have decided to pick this 4th index, obviously you will move to the 5th index, right? Now what are the other options? Can you pick this 3 up? So imagine if you're picking this 3 up, again you're creating a data structure which is having this 3. So you're generating a list of size 1 which is containing 3. So that means a duplicate again. So there's no need to call this recursive function. So we do not call this. So basically we are getting an idea, right? So if there are duplicates, only pick up the first time the 3 is occurring, not after that, right? So let's not pick it. So let's see beyond this. So you have called this recursion, right? What after this? So I'm currently standing at the first index and my list is of size 1. Now I'm planning to extend this list beyond size 1. I want to make it a size 2 list. So what are the options? Can I pick this 2 up? Obviously you can. So if you decide to pick this 2 up, your data structure will now contain 1 and 2. And you can say that you got a list of size 2 which is containing 1 and 2. So if you decided to pick this 2, that is index 1, you'll move to the next index, that's 2, right? What other options do you have to create a size 2 list? Can you pick this 2 again? Now imagine if you decide to pick this 2. So you will have a data structure which is containing 1, 2. So you are regenerating this list again. So you're getting an idea, right? There's no need to pick up the duplicates. So we avoid this. Will you pick this 2? Obviously no. Will you pick this 3? Yes, because you're getting another list of size 2 which is 1 and 3. So that's a unique list. So we can take it, right? So I'm taking that. So if you're taking that, to which index will you move? So I've decided to pick up the 4th index. So you'll move to the 5th index because 4th index cannot be picked more than once, right? So you have picked up this 3. Can you pick this index 5, 3? Obviously no, because you're trying to create a list of size 2. So if you decide to pick this 3 again, you're going to get this 1, 3 again. So there's no need to pick this up, right? Let's understand this. So you are having a list of size 1 which is having 2. So now let's try to create a list of size 2. So what are your options? Can you pick this 2? Now you might say it's going to be a duplicate. Doesn't matter, because this is the first time you're picking up a new index. You're currently at the second index, right, which is this. So this is the first time you're picking up this 2. So if this is the first time you're picking up this 2, so you will get this list for the first time, which is 2 2. Now in the next time, yes, in the next time when you'll try to pick this 2, then you'll get a repetitive list. Understand? So that means if this is the starting index, you don't look for duplicates, you pick it, because this is the first time this is getting involved in making a list of size 2. So that's why you pick it. So if you pick the index 2, you'll move to index 3. Now the question, will you pick this 2? Obviously no, because you're standing at 2 that had 2. So this 2 will not be picked, because if this gets picked up, you'll again get 2 2, which doesn't make sense, right? So if you cannot pick this 2, can you pick this 3? Obviously yes, because that's the first time you're getting a 3. So if you pick this 3, your list will have 2 3. So I can see another list of size 2 that you have generated. So I can say that since you're picking a 4th index, you'll move to the 5th index, right? Now over here, you're having a list of size 1 which is having 3, and you're standing at the 5th index. So can you pick this 5th index up? I know this 3 is a duplicate, right? But can you? Yes, because this is the index where you start. And you know, whenever you start, so this is the first time you're going to pick up a 3 for a size 2. This is the first time you're going to pick up a 3 for a size 2, not the second time. So you pick this up, so you will get 3 3. So since you picked the 5th index, you move to the 6th index. So I can say another list of size 2 has been generated, which is 3 3. So this level of recursion calls is making sure that all the lists of size 2 are generated. So the first level of recursion did make sure empty subset was generated. The second level of recursion made sure that all the subsets of size 1 are generated. The next level made sure that all the sizes 2 are generated. So what will the next level make sure? It will make sure that all the list of size 3 are generated, right? So let's do that. So if I'm having a data structure of 1 2 and I'm standing at the second index, so that's the first time I'm trying to make a list of size 3. So if I'm trying to make a list of size 3, can I pick this 2? I know it's a duplicate, but this is the first time I'm picking a 2. So let's pick this. So you get 1 2 and 2. So if you're picking the second index, you'll move to the third index. So in this way, you generated a list of size 3, correct? So let's generate this. Next time, let's see. Can you pick this 2 now? That's the question. Obviously not, because you're trying to make a size 3 and you've already picked up a 2 while making size 3. There's no need of again picking up 2 in order to make a size 3, because that's going to generate the same list. Because if you try to pick this third index, you're again going to get 1 2. And since you're picking up the 2, you get 1 2 2, which you have already generated. So you ignore this. Can you pick this 3? Yes. If you decide to pick this, you'll get 1 2 and a 3. So this will be another list of size 3 that will be generated, correct? Which is 1 2 3. And since you're picking up the 4th index, you will move to the 5th index. Now my question to you is very simple. Can you pick this 3? Obviously no, because we have tried to make a list of size 3 and you've already picked 1 3. So there's no need to pick another 3 for it, right? So you don't pick it up. Now you're at the 5th index, and this is the first time from this recursion you're trying to make a list of size 3. First time. So if this is the first time, do you check out that whether you've picked it previously? No, there's no need to check out, because this is the first time. So if it is the first time, don't think anything, just pick up the first index. That's a 3. So you're getting another sub list of 1 3 3. So if you're picking up the 5th index, you're actually moving to the 6th index. And the moment you have moved to 6th index, I can say after this recursion call, you cannot generate a list of size 4. Yes, from here you can generate, but beyond this, there will be no generation. Similarly, you can do it for this and you'll get a list of size 3. Similarly, from here, you can call it and you'll get a list of size 3. And you can keep on doing. In the next level, you'll get all the 3 size sublist. Again, if there are any further recursion calls, in that you will get all the sublists of size 4, and if there are any further recursion calls, you'll get all the sublist of size 5, and if there are any further, you'll get it for size 6. Sixth will be the last recursion call that will be made because n is 6. But over here, since there are duplicates, you'll not go till the 6th level of recursion call. You will stop much before that. I'm not going to draw the entire recursion tree because there are a lot of sublists that this test case will generate. So it's going to take a lot of time. But you understood, right? At the first level, you try to generate a list of size 0. At the next level, you try to generate a list of size 1. Then you try to generate all the lists that are of size 2. Then you try to generate all the lists that are of size 3. So every time you call a recursion, the sublist that you're getting will be among one of the subsets that you are wanting to generate. And it's a very easy way. Avoid picking up duplicates so that you only generate unique subsets. So this was about the recursion tree. What about the pseudocode? Let's understand the pseudocode. So we can say that the initial call obviously will be something like this can be said as index and this can be said as a data structure. So imagine we are currently standing at an index and we have a data structure. Now this data structure can be of a 0 size, can be of a size 1, can be of a size 2, doesn't matter. But that's the general convention of the recursion call, isn't it? So what are your options? Now this data structure, just imagine this is of a size S. Now you know in the next recursion call, you're going to make this data structure into a size S plus 1, right? You're going to increase the size by 1. And obviously, whichever index you pick, like over here, you decided to pick this 3, which was a part of the 4th index. So you decided to pick the 4th index. Over here, you picked this 2, which is the 1st index. So I can see if I'm picking any index I, right, I am moving to I plus 1. Do you see this? If you're picking 1, because you've picked up 1, the next picking up will start from 2. So you're actually calling the recursion for I plus 1. So I can say this is the transition of recursion. And where can this I range from? Can I say the I will range from index to n minus 1? Obviously, because see, if you're at the 0th index, you can decide to pick the 0th index. Then you can decide to pick the 1st index. Then you did not pick the 2 and 3. The reason was they were duplicates, right? That is why you did not pick them. And then you picked 4th, but you did not pick 5 because it was duplicate, right? Similarly over here, when you had 2, you picked the 2nd index, then you picked the 4th index. And in between, you did not pick the 3rd index because 2 was giving you 2. After that, 3rd would have given you 2 again, C. So you did not pick it. So I can say, I will be this, avoiding duplicates, right? I will always be that index which does not have duplicates. So you can pick it. So if you're picking up, so I can say my data structure will obviously add the value array of I because you're picking that up. So every time you add that, your sublist size is going to increase by S plus 1. So your transitions are very simple. Every time you get a data structure, you basically iterate from index to n minus 1. And if it's possible to pick, if that's not a duplicate, you decide to pick it. So if you're picking up the ith index, you move to the next index because that is where you can start picking up in the next recursion. So once you have picked up I know you cannot pick up I anymore. So you move to the next index, that's I plus 1. And your data structure is going to add the element that you're picking up. So your data structure has an increase of size plus 1. So this is going to be the transition, right? And to avoid duplicates, it's very simple. If it's the 1st index, that is the 2, you don't need to think anything, just pick it up. After that, if it is the 3rd index, just check it. If this 2 is equivalent to this 2, don't pick it and you move ahead. Simple, just check. If it's not the 1st index that I'm trying to pick, just check if that's equal to the previous. If that is, that means it would have been picked up to make a data structure, to make a subset of a particular size. So no need to pick. So this is going to be the transition. Now since we are generating 2 to the power n subset, so the time complexity again will be 2 to the power n for this particular recursive call. Now every time you're getting a subset, right? Every recursion call is giving you a subset, that is ds. So this ds will be put into some answer data structure, right? Every time you're getting an first time you got an empty data structure, then a single size, then a single size, then a size 2. So every time you're getting a data structure, right? So you're putting it into some answer. So this putting will take some time. It's not a big of fun operation. So assuming that the average length of every subset is near about n by 2 or something, let's say it's near about n only. So that's gonna take 2n into n, assuming that every subset is near about size n. So it's gonna take n time to put into your answer subset. So that's a deep copy that you're making. So 2 to the power n for recursion, n for copying that subset that you're generating. So that's the time complexity for the recursion. What about the space complexity? At worst, you're gonna make 2 to the power n subsets. So you're gonna store that in your answer. So 2 to the power n subsets, and everyone will have an average length k. So everyone will have an average length k. So I can say average length k. So yeah, that's gonna be the space complexity to actually store all the subsets, and the auxiliary space of recursive call will be big O of n, because that is the depth of recursion which it will go at maximum 6 depth, you saw. So that will be the auxiliary space that the recursion will require. So that's the time complexity, space complexity, and the auxiliary space complexity. So now it's time to discuss the C++ as well as the Java code. So let's understand the Java code. So in the Java code, you can see that they're asking you to return a list of integers, right? And they're just giving you the nums array. So at first, what you will do, you will sort the nums array. Now I did not tell you this, but in order to have all these duplicates in side by side, you need to sort it, right? Otherwise, how will you get the duplicates in side by side, and how will you apply your recursive logic? So please make sure whatever input is given to you, sort it. After this, you can declare a list of answer, which is the ultimate data structure, which is gonna store all these lists, right? So I've done that. Once you have done this, what's your next objective? Let's call the recursion. Now you know what is the initial state. Initial state is 0 with an empty data structure. So let's call it with an 0 and an empty data structure. So this is the recursive call. So you always know whenever a recursive call is made, this becomes a part of your answer, because this is a list with a size 0. So this is what I do. I make a deep copy of ds and I add it to our final answer. Right after this, what do? We know we're going to start checking from 0, 1, 2, 3, 4, 5. That's basically from index to n-1. So let's start checking from index to n-1. For a moment, let's forget this. I'm going to explain you this after this. So if you're moving from index to nums length -1, assume you have crossed this if. If you have crossed this if, it means you're liable to take this element and make this data structure of size +1. So you pick this element and add it to your data structure. And since you have picked up the index I, please make sure you move to the next index I+1. That is what the transition is. And you just pass on the data structure, which has this added. But whenever you come back from the recursion, please make sure this last element that you added is removed, because for the next recursion calls, it should not be there. So that's how your recursion will work. So anytime you get something like 6, right? So this list will be added to your answer list. When you enter your recursion, this will be added, and this for loop will not run, because the for loop will be running till n-1. And this is 6, so it will not run. So automatically it will end over here, and it will not call any further recursions. But now let's understand about this. Okay, so imagine this is the recursion call, right? The recursion call f2, and you're having 2 in your data structure. So you are having the index 2. So you know the looping will run from 2 to the end, correct? So 2 is basically this guy. So this is a duplicate of this 2, but you are still picking it up. So this is the condition that I've written. If that's not equal to n, that means if it's equal to n, you can pick it. So if that's not equal to n, why this? Just assume that at the first time you decided to pick the second index. Next time for the third index, when you come up, right, this is for this, so you will not be picking up this, right? So if this 3 is not equivalent to this and it's a duplicate, this 2 is equivalent to this 2, so let's continue. I'll not be picking up. So if it is not the first and if it's the duplicate, let's continue. But if it is the first, let's pick this 2 and put it into our data structure to get this. So this is what this if statement means. So once you have executed this, all of these will be generated and you'll get all your subsets of every size. So once you have got that, your recursion will be over and you can return your answer list, which will be your ultimate answer. Now let's discuss the C++ code. So in the C++ code, you can see they're asking you to return a vector of vector, which will be your ultimate answer. So they've given you the nums array, right? So what we do is we initially take an answer array. So this answer array is going to store all these subsets generated into a final data structure, which is answer. And right after this, we declare an empty data structure, which will be used over here. And we make sure that we sort the given array. Now why do we sort that? If we do not sort that, these twos will not be together and we cannot apply our logic in the recursion that we discussed, because for that we want the duplicates to be together. So if you sort them, the duplicates will be together. Right after that, I will call the recursion. What is the initial state of recursion that we started? We initially started at the 0th index and we assumed that nothing was picked, right? That's an empty data structure. So let's call it with 0 and the empty data structure. And along with it, let's carry the nums array and the answer array, which will be our ultimate answer. So let's see what's happening inside our recursion. So whenever the recursion is called, at the first step, we are seeing that it's taking the data structure and putting it into the answer. So this is where the extra time that I talked about of n of making the deep copy is going, right? So you are generating this ds into the answer. So first time you got an empty data structure when you call the recursion. So you put it into the answer. Next time you pick this and you call this, you got this. So you pick it up and put it into your data structure. So this is what the line number 4 does. Right after that, you know the transition. This is index, this is dx. What is the transition? You always iterate from I equal to index to n minus 1. Basically saying if you are at 0, you try the 0th, you try the 1st, you try the 2nd, you try the 3rd, you try the 4th. Whichever you can pick it, you pick and you call the next recursion. So for a moment, let's forget this line. For a moment, just ignore this line. So if you can pick that index I, right? If you can pick this index I, you put it into your data structure. So this is what this line does. Put it into your data structure. Right after that, you call the recursion. And where do you call? To the next index from where you can start picking up. So if you have picked up the ith index, obviously you cannot pick it again. So you move to the next index, that is I plus 1. And you make sure you carry the data structure. But please be careful that whenever you come back, remove the guy that you have added, because for the next recursion call, you don't want the guy to be kept on that data structure. Please make sure you remove it. So you've understood this step. But what about this non-picking step? Let's understand. Imagine the recursion call was made for f of 2, that's the second index, and the data structure was 2. So the array was like 1, 2, 2, 2, 3, 3. That's 0th index, first index, second index, third index, fourth index, fifth index. So this is the 2 where I'm currently standing. So can you pick this 2? The answer will be yes, I can pick the second index. Next will be, can I pick the third index, this one? The answer will be no, I cannot pick. Why? Because if I again pick it, I'll get the same data structure. So this is why the first condition, if they're equal, if it's equal to the previous, let's have a continue. But wait. This 2 is equal to this 2. So why did you pick it? So that is why I said, if that's the first index, you pick it. Because this is the first time 2 is getting picked. So that is why I wrote, if I is not equal to n, then only continue. But this 2 is equal to n. So I will go and pick it up. So I hope you have understood. If you did not, go back, watch it again. You will surely understand. So once this entire recursion is over, you must ask that why is there no base case? So imagine every time a recursion call for something like 6 is made. So will this loop run? No, because this loop is still n minus 1. So this will only make sure that this data structure is added to your answer. And after this entire for loop will never run and your recursion is over. So there's no need to write a base case, right? It automatically gets over. So once the recursion gets over and all the recursion call for all the levels are made, you can return your answer, which is your ultimate answer, right? So that will be it for the C++ code. So guys, I hope you have understood the entire explanation as well as the code. So just in case you did, please make sure you like this video, and if you're new to our channel, please do subscribe to this channel. It will be of great help. With this, I'll be wrapping up this video. Let's meet in some other video where I'll be solving something other from the SDE sheet.